to the wheel, a small air plenum is formed in between. The rotor internal cooling air, which passes through slots on the forward face of the first wheel spacer, is fed into these plenums. Cooling airflow from this plenum to a series of longitudinal air passages to cool the bucket and exit at the recessed bucket tip. Buckets are attached to the wheel by straight axial entry multiple tang dovetails that fit into matching cutouts on the wheel rims. The buckets are prevented from moving axially by the D-key arrangement. A radial locking pin is installed before the first bucket. Then, the first bucket is installed and locked in place by the D-key. This is repeated for the next 90 buckets. The last bucket is installed, and an axial locking pin is inserted on the locking bucket dovetail. This pin pushes the radial locking pin to hold the last bucket on position. The first wheel spacer is located between the first and second turbine wheels. Spacer function is to define the axial position of the turbine wheels. The outer diameter of the spacer carries the diaphragm sealing lands. Slots are machined on both forward and aft faces for cooling functions. The second wheel carries the buckets of the second turbine stage. 92 buckets are also installed on the second wheel. Buckets are attached to the wheel by the same dovetail arrangement of the first stage, but they are held on the axial direction by twist locks arrangement. Twist locks are first placed on the wheel. Then buckets are installed as a 360 degrees ring due to the interlocking between the buckets. Once the buckets become on position, the twist locks are rotated and stacked. Buckets are internally cooled by the rotor internal cooling air, which passes through slots on the aft face of the first wheel spacer. This air is fed into a plenum casted on the bucket shank. From this plenum, air flows into span-wise holes machined on the bucket and exits at the bucket tip. The second stage bucket tip is enclosed by a shroud, which is a part of the tip seal. These shrouds interlock from bucket to provide vibration damping. These shrouds also feature the cutter teeth, which open slot on the honeycomb seal and mates with the seals on the shroud block. The second wheel spacer is located between the second and third turbine wheels. Slots are machined on the forward face. The forward face of the spacer is machined to form a gap at the mating surface with the second stage wheel for cooling functions. The third wheel carries the buckets of the third turbine stage. 92 buckets are also installed on the third wheel. Third stage buckets are not internally cooled. Third stage bucket tip is also enclosed by a shroud. Buckets are attached to the wheel by the dovetail arrangement and held on the axial direction by twist locks arrangement like the second stage. The aft wheel shaft is machined to provide the following features: journal surface for bearing number 3 and surfaces for oil and air seals, aft balancing groove, aft flange to connect the turbine rotor to the generator rotor. The turbine rotor must be maintained at reasonable operating temperature to assure a longer turbine service life. For this purpose, bucket vanes are not directly attached to the dovetail. Instead, they are connected to their dovetails by means of shanks. These shanks locate the bucket to wheel attachment at a significant distance from the hot gases. Combined with the diaphragm segments, this arrangement isolates the rotor away from the hot gases flow. Seals from the first stage nozzle support ring mate with sealing wings extruding from the forward side of the first stage bucket shank. Also, seals from both sides of each diaphragm mate with sealing wings from both sides of each bucket. The seal from the exhaust frame mates with the sealing wing on the aft side of the third stage bucket shank. All these seals reduce leakage of the hot gases radially inward to rotor parts, improving turbine efficiency and protecting the rotor parts. The rotor parts are cooled by positive flow of cooling air discharged radially outward through a space between the turbine wheels and the turbine stator parts. These spaces are called the wheel space. The first stage forward wheel space is cooled by compressed air leaking from the high-pressure packing at the forward end of the inner barrel. The first stage aft wheel space is cooled by the compressor discharge air supplied through the second stage nozzle. The second stage forward wheel space is cooled by a portion of the first stage aft wheel space cooling air, which passes through the labyrinth and brush seal. The second stage aft wheel space is cooled by the rotor internal cooling air, which passes through the slots on the forward face of the second wheel spacer. The third stage forward wheel space is cooled by a portion of the second stage aft wheel space cooling air, which passes through the labyrinth seal. The third stage aft wheel space obtains the cooling air from the exhaust frame cooling system. The rotor internal extraction cooling air is utilized for bucket and wheel space cooling. This airflow also maintains the parts of the rotor at approximately compressor discharge temperature. This ensures longer service life for turbine rotor parts. For efficient gas turbine operation, clearances between all rotating and stator parts should be tight as possible. As the turbine shell controls the radial and axial position of all turbine stator parts, the shell should be isolated from the high temperature of the enclosed hot gases. This will ensure the control of the shell diameter and roundness to be maintained. The heat transfer from hot gases is reduced by the following means. Hollow shroud blocks provide high thermal resistance between the hot gases and the turbine shell. The first stage shrouds are cooled by the compressor discharge air. The third stage shrouds are cooled by cooling air from the cooling and sealing system. This air is extracted from the compressor fifth stage and supplied to the third stage shrouds through 6 holes machined on the turbine shell. Combined with the assembly of the nozzles between shrouds, hot gases are kept away from the shell. Heat transfer from the nozzle segments to the shell is reduced by means of insulation packages. The external surface of the turbine shell incorporates cooling air passages. Cooling air is supplied from the exhaust frame cooling circuit. To control the amount of airflow, multiple metering orifices are installed on the flow passages. The exhaust assembly consists of 2 parts, the exhaust frame and the exhaust diffuser. The exhaust frame consists of inner and outer cylinders connected together by 10 radial struts. The inner cylinder supports bearing number 3. The lower part of the outer cylinder features mounting points for the turbine aft legs and the jib key. The inner side of the exhaust frame parts is covered by the inner and outer diffuser. The outer diffuser surface is manufactured to provide divergent cross-sectional area to increase the exhaust gas's pressure. The struts are covered by airfoil-shaped fairing surfaces. The inner and outer diffuser and the airfoil-shaped fairing surfaces are metal surfaces which protect the exhaust frame parts from being exposed to the high temperatures of exhaust gases to maintain temperature stability. This stability is required to keep the exhaust frame inner cylinder, which carries the bearing number 3, in the accurate position, avoiding any misalignment. To ensure the temperature stability, air is forced by means of two off-base blowers between the exhaust frame outer cylinder and the exhaust frame diffuser surface through 4 ports. A portion of this air goes to the cooling holes around the turbine shell, and the remaining air flows between the struts and its outer airfoil-shaped fairing surface. Then, cooling air exits in 2 directions, to the third stage aft wheel space and to the inside of the inner cylinder around bearing number 3 to protect the instrumentation in this area from being exposed to high temperatures. The portion of the exhaust frame inside the exhaust plenum, which is exposed to exhaust gases, is covered by insulation packs to reduce heat transfer. The exhaust diffuser is located at the extreme aft end of the gas turbine, bolted to the exhaust frame. The exhaust diffuser is a fabricated assembly consisting of inner cylinder and outer divergent cylinder. This divergent configuration reduces the exhaust gas's velocity and increases its pressure. At the aft end of the diffuser, 5 turning vanes direct gases from the axial to the radial direction into the exhaust plenum. The inner side of the inner cylinder is isolated by insulation packs to reduce the heat transferred to the load coupling tunnel and to the bearing number 3 area. The gas turbine rotor is supported by 3 bearings. These bearings hold the rotor in the radial direction by journal bearings and in the axial direction by thrust bearings. Bearing 1 is located in the center of the compressor inlet casing and held in place by straps. The bearing components are installed inside the bearing housing, which consists of the lower and the upper halves. This bearing contains an elliptical journal bearing, loaded thrust bearing, and unloaded thrust bearing. Labyrinth seals are installed at each end of the housing, where oil control is required. Their teeth run against smooth surfaces machined on the rotor. Seals are assembled so that a small clearance exists between the seals and the shaft. The sealing airflow from the cooling and sealing system through the axial tube machined at the right side of the housing and is admitted to the labyrinth seals through 2 ports to annular spaces surrounding the seals. Between the 2 rows of seal teeth, sealing air is admitted through multiple radial holes to stop oil from spreading along the shaft. Some of this air returns with the lube oil and is vented through the lube oil mist eliminator, and some escapes out of the housing. Inboard of the main pressurized seals, 2 backup labyrinth seals are installed for positive sealing. A floating seal is installed on the forward of the thrust bearing cavity to contain the oil. The journal bearing components are the bearing liner and the journal surface machined on the compressor forward stub shaft. The bearing liner consists of 2 halves fitted on the bearing housing. The liner inside faces are machined to make convergent oil clearance, in which oil pressure increases around the shaft journal to support it. After machining, these faces are coated with Babbitt alloy. For lubrication, oil is supplied through the oil feed pipe to a port in lower bearing housing, where the oil fills an annular space around the liner and is admitted inside the liner through 2 grooves machined at the horizontal matching edge. Oil is drained through the vertical drain slot at the bottom of the lower liner half to the journal drain cavity down to the oil drain piping. The thrust-bearing major components are the thrust runner, which is integrated in the compressor rotor forward stub shaft, and 2 thrust bearings. During the normal operation of the gas turbine, the sum of axial forces induced by the airflow on the compressor stages and the hot gases flow through the turbine stages tend to move the rotor in the upstream direction, so that the active thrust bearing is located on the forward side of the thrust runner. While in the transient operation during startup and shutdown, the shaft tends to move in the downstream direction, where the inactive or unloaded thrust bearing is located. The active thrust bearing is a tilting pad equalizing type bearing. An equalizing type bearing is capable of sustaining high axial loads and is tolerant of shaft and housing misalignment. The main components of this bearing are the base ring, the tilting pads, upper leveling plates, lower leveling plates, shim plate. The base ring provides support for all parts of the bearing assembly and keep parts in the proper location. The pads are shaped like a sector of a ring. The bearing surface is covered with Babbitt alloy. Every pad has a hardened steel button on its back called the pad support. This pad support allows the pad to tilt slightly in any direction. The leveling plates are functionally small levers. They align the bearing pads with the thrust runner and equalize the load among the pads despite any possible slight misalignment of the shaft axis from the normal. The leveling plates are mounted on the base ring by dowels and screws, such that the plates are free to tilt on their fulcrums. The load transmitted by the thrust runner to a single pad causes the pad to press on the upper leveling plate right behind it. Each of the upper leveling plates in turn is supported by one edge of 2 lower leveling plates. The other edges of the lower leveling plates take part in supporting the adjacent upper leveling plate on either sides. As a result of this arrangement, any excess of thrust load on a single pad is immediately shared through the leveling plates, so that all bearing pads will automatically receive equal loading. For lubrication, oil is supplied through the oil feed pipe to 2 ports in the lower bearing housing, where the oil flows into annular space around the base ring. Then, oil flows through grooves machined on the back side of the base ring to the bearing cavity, where it is carried by the pumping action of the thrust runner to the entire bearing surfaces. Oil exits at the pad's periphery to the thrust bearing drain cavity down to the lube oil drain piping. The inactive thrust bearing is a tilting pad non-equalizing type bearing. A non-equalizing type bearing is also capable of sustaining high axial loads, but less tolerant of shaft and housing misalignment. This bearing is functionally identical to the active thrust bearing, except that it doesn't have leveling plates. Instead, the tilting pads are directly supported at their back by the base ring. Oil control plates are installed between pads. For lubrication, oil is supplied through the oil feed pipe to a port in lower bearing housing, where the oil flows into annular space around the base ring. Then, oil flows through holes on the back side of the base ring to the oil control plates, which introduce the oil directly to the bearing surface before each of the pads. Oil exits at the pad's periphery to the thrust bearing drain cavity to the lube oil drain piping. Bearing 2 is located in the center of the inner cylinder of the compressor discharge casing and held in position by straps. The bearing components are installed inside the bearing housing, which consists of the lower and the upper halves. Bearing 2 is located in a pressurized area between the compressor and the turbine. This compressed air is leaking from the high-pressure packing at the aft end of the compressor shaft. Labyrinth seals are installed on both ends of the housing to prevent this air from leaking inside the housing. Since any air leakage past these seals doesn't perform any additional work, any reduction in this flow will result in an increase in the unit performance. A brush seal is installed on both labyrinth seals to minimize air leakage as much as possible. Bearing 2 has a vented cavity. The compressed air leaking from the outer labyrinth seals is vented to the atmosphere through a vent pipe mounted on the top of the housing. Inboard of the outer air seals, 2 pressurized labyrinth seals are located for lubricant control. Sealing air supplied through a pipe concentric with the vent pipe fills the sealing air cavity. And flows between the 2 rows of each of the labyrinth seals. Some air escapes to the vented cavity, and the remaining returns with the lube oil. The journal bearing components are the bearing liner and the journal surface machined on the turbine forward wheel shaft. As the upper and lower housing parts are not symmetric around the liner, a liner strap is installed on the top to provide support for the liner and form the annular space for lube oil flow. For lubrication, oil is supplied through the oil feed pipe to a port in the lower bearing housing, where oil fills the annular space around the liner and is admitted inside the liner through 2 grooves machined at the horizontal matching edge. Oil deflectors are mounted on both ends of the liner to help containing oil inside the liner. Oil is drained through the vertical drain slots at the bottom of the lower liner half to the lube oil drain cavity, down to the oil drain piping. The number 3 bearing is located at the aft end of the turbine, in the center of the exhaust frame. The bearing components are installed inside the bearing housing, which consists of the lower and the upper halves. Bearing 3 is a tilting pad journal bearing. This type of bearing is used in situations where slight misalignment is expected. Labyrinth seals are installed in housing where oil control is required. Their teeth run against rotor smooth surfaces. The sealing air flows from the cooling and sealing system through the axial tube machined at the left side of the housing and is admitted to the labyrinth seals through 2 ports to annular spaces surrounding the seals. Between the 2 rows of seal teeth, similar to other bearings, sealing air is admitted through multiple radial holes to stop oil leakage. Some of this air returns with the lube oil, and some escapes out of the housing. A forward air deflector seal is installed at the forward side of the housing to prevent crossflow, and vent holes are machined on the housing. The bearing liner of the tilting pad type consists of a retainer ring and 5 tilting pads. The tilting pads are assembled so that high-pressure oil film is generated between each pad and the rotor journal surface. This produces symmetrical force on the bearing surface that helps to maintain shaft stability. Each pad is mounted to the retainer ring by 2 pins and supported from the backside by a pivot pin. This configuration allows the pad to rotate in 2 dimensions. This movement makes this type of bearing capable of tolerating small amounts of shaft misalignment. For lubrication, oil is supplied through the oil feed pipe to a port in the lower bearing housing. where oil fills an annular space around the liner retaining ring. Oil is admitted inside the liner through 5 orifice holes, machined radially on the retainer ring to the gaps between pads. 2 floating ring seals are mounted on both ends of the retainer ring to maintain an adequate amount of oil inside the liner assembly. Oil is drained through the vertical drain slots at the bottom of the lower retainer ring half to the oil drain cavity, down to the oil drain pipe.